Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss HUYGEN'S eyepiece. Let's begin. Basically, eyepiece is a specially designed which gives a more perfect and magnified image as obtained by a single lens of equal focal length, and it consists of two converging lenses, and these lenses are separated by a certain distance, and the lens towards the object is called field lens, and other lens towards the eye is called eye lens. And the focal length of field lens and eye lens and the separation between them such that it avoids chromatic and spherical aberration should be minimum. For that purpose, we use eyepiece as it provides magnified image produced free from chromatic and spherical aberrations, and the field view of image is so large. What is chromatic aberration and spherical aberration? Look here. Spherical aberration, if we take a concave mirror, let having large spherical surface, that be the focus, if ray of light parallel to that principal axis, then it passes through that of focus. But due to large sphere, exactly the rays which are parallel to that of principal axis not passes to the focus, that is before the focus or after the focus. That is, the process is known as spherical aberrations, and that aberrations can be avoided by adjusting the focal length of field lens and eye lens in case of eyepiece. Again, chromatic aberrations, if similar thing, if we take a lens and the rays which are parallel to that of optical axis, then that rays pass through the focus, but due to the white light and the process of, or we can say the phenomenon of dispersion, that white light split off into respective colors, that means the colors like vivier, and these colors are not exactly at the point of focus. That is the process of chromatic aberrations. So, the chromatic aberration and spherical aberrations can be avoided by placing field lens and eye lens with corresponding positions. Now, the eyepiece are various types. Here we discuss about HUYGEN'S eyepiece and Ramstead's eyepiece. In this particular video lecture, we discuss about HUYGEN'S eyepiece, its construction and working. In next video, we discuss about Ramstead's eyepiece. Let's start. HUYGEN'S eyepiece. The construction of HUYGEN'S eyepiece, it consists of two plano-convex lenses that made up of same material, and the focal length of field lens and eye lens, the focal length of field lens is 2f and focal length of eye lens is f, and these two lenses are mounted coaxially with their convex faces turned towards the incident light. The field lens and eye lens are separated by a distance 2f. So, the construction of Huygens eyepiece the plano convex lens, that is the field lens, that one is the eye lens. These two are separated by a distance of 2f. The field lens have the focal length 3f with the focal length of 3f. Eye lens have the focal length f, that be the position of equivalent focal length. Equivalent focal length. Now we discuss what should be the working process throughout this working process. Let the optical instrument is placed with its objective facing the object. In that of particular figure, there will be no such objective, and the working of that objective is to converge the beam coming from object on the field lens of eyepiece. So, in that figure there will be no such objective, and the working of that of objective is to converge the beam coming from that object on that of field lens. So, the rays are coming from objective to the field lens. And this due to this objective, the image I1 is formed by the objective which serves as the object for the field lens, and the image I2 is formed by the field lens, and the image I2 lies in the first focal plane of the eye lens, and the final image is formed by the eyepiece at infinity. So, look here, here the rays. That is the image I1, which is the object for that of field lens. So, here the images are formed that image, that is I2, okay. Image is formed at the eye. Next, how the chromatic aberration, or what should be the condition for achromatism, here chromatic aberration is that is the condition for chromatic aberration. Condition for chromatic aberration so the distance must be the sum of these focal lengths divided by 2. Here f1 is equal to 3f, f2 is equal to f divided by 2, that is the focal length of field length, which is 3f, focal length of eye length, which is 1f. So the distance between these two lengths, that is 4f divided by 2, which is equal to 2f. So to avoid chromatic aberration, the distance must be 2f in between field lengths and eye lengths. Okay. Next, for spherical aberration, condition for spherical aberration the separation between these two lenses must be f1 minus f2. Here f1 is equal to 3f, f2 is equal to f, therefore d is equal to 2f. Again, as the distance between field length and eye length is 2f, therefore it avoid spherical aberration. Next, optical separation between the two lenses. Optical separation between the two lenses. Let optical separation between two lenses delta is equal to f1 plus f2 minus d, or delta is equal to f1 3f plus f2 f minus d is equal to 2f. Therefore delta is equal to 4f minus 2f, that is optical separation also 2f. So this is the condition for chromatic aberration, condition for spherical aberration and optical separation. So the distance between the field length and eye length must 2f as we situate these two. Next, the distance of field length from the image I1. Distance of field length, let u, that is the image distance, sorry, u, that is the object distance from the image I1. How to calculate? From lens formula, 1 by V minus 1 by U is equal to 1 by F1, its focal length. Again using the proper sign convention, V, that is the focal length F, U, that is calculated, then F1, that is 3F. Therefore 1 by U is equal to 1 by F minus 1 by 3F, or 1 by U is equal to 3 minus 1 divided by 3F, or 1 by U is equal to 2 by 3F, or U is equal to plus 3 by 2F. This shows that this, which implies the image I1 due to the objective lies on the same side of the field length as image I2. So here that be the distance is equal to 3 by 2 F. Here is the distance F, that be the distance F. Okay, that is 3 by 2F, 3 by 2F. Next, position of crosswire. Position of crosswire. Where should be the position of crosswire? In that of particular case, crosswire must be placed in the position of real image, that is I2, which is the midway between, that is the midway between the field length and eye length, the field length and eye length. However, particularly in case of HUYGEN'S eyepiece, however, crosswire not provided in this eyepiece. In this HUYGEN'S eyepiece, crosswire not provided. If the crosswire will be there, that be at I2, which is exactly the mid position of field length and eye length. The distance is 2F and that distance is F. Next, calculating the equivalent focal length. What should be the equivalent focal length due to these two lenses? That equivalent focal length can be calculated by using the concept of system matrix. So, in this case, the system matrix when two thin lenses are combined, then what should be the matrix representation of that system matrix? Look here, a simple thing. If two thin lenses, it has the focal length f1, it has the focal length f2, and these two are separated by a distance let d. Then at that surface, due to the thin lens, here t tends to 0, and at that particular plane the phenomenon of refraction takes place, within this translation takes place, and that surface the phenomenon of refraction takes place. So, here we get the matrix for refraction, here the matrix for translation, here the matrix for refraction also. So, the system matrix here if we calculate the system matrix, then it will be the system matrix SM, that surface refraction takes place. So, in case of thin lens, the matrix be 1 0 minus 1 by f2 1. Here translation, thickness distance be d, therefore for translation the matrix 1 d 0 1. Again for refraction it will be 1 0, its focal length 1 by f1 1. Now we use the matrix multiplication like this. So, 1 0 minus 1 by f2 0, here for matrix multiplication 1 minus d by f1 d minus 1 by f1 1, again matrix multiplication, that is 1 minus d by f1 1 minus d by f1, again that row to this column, that is minus 1 by f1 plus d by f1 f2 minus 1 by f2. Here is the f2, that is f1, here d minus d by f2 plus 1. Now write it systematically. So, the system matrix SM be 1 minus d by f1 d minus 1 by f1 minus 1 by f2 plus d by f1 f2 1 minus d by f2. In that of particular case, here f1 is equal to 3f, f2 is equal to f, and d is equal to 2f. Now all these values are put here. So we have the system matrix SM 1 minus 2f by 3, 2f by 3f, that is 2f minus 1 by 3f minus 1 by f plus 2f divided by 3f into f 1 minus 2f by f, which is equal to 1 by 3 2f minus 2 by 3f minus 1, that is for SM. Now we compare it to the system matrix. As you assume, we know the system matrix SM, the components like A, B, C, D, but in that of case we take dB the distance between these two lenses, therefore here I prefer D dash. Now comparing these two, comparing 1 and 2, comparing 1 and 2, we get the matrix components like A is equal to 1 by 3, B is equal to 2f, C is equal to minus 2 by 3f, and D dash is equal to minus 1. By using these matrix components, we can easily calculate the equivalent focal length and the location of cardinal points. Now we can easily calculate the equivalent focal length. So the equivalent focal length is 1 by f, which is equal to minus c, as we studied in case of locating the cardinal points by using system matrix. These formulas are studied. Here I can use 1 by f is equal to minus 2 by 3f, or f is equal to minus, that is minus c minus 2 by 3f plus 3 by 2f, that is the equivalent focal length. Next, the calculation of cardinal points. What will be the location of cardinal points? Locations of cardinal points. There are 6 number of cardinal points as 2 focal points, 2 principal points, and 2 nodal points. First, focal points. By using the components of system matrix, we can calculate the focal points. Let that focal points are their corresponding distances x1 and x2. So x1 is the first focal point, that is d dash by c, which is equal to minus 1 divided by minus 2 by 3f, which is equal to 3 by 2f, and x2, which is minus a by c, it is minus 1 by 3 divided by minus 2 by 3f, which is equal to 1 by 2f. It is x1 is equal to 3 by 2f, x2 is equal to 1 by 2f. x1 is the first focal point, location of first focal point, that is the location of second focal point f2. Next, nodal points. Location of nodal points. Nodal points, basically 2 nodal points n1 and n2, which is at a distance of t1 and t2. So again t1, that is d minus 1 by c, at that case we treat d dash, so put that value minus 1 divided by minus 2 by 3 f, so minus 2 divided by minus 2 by 3f, or 3f, and t2, that is 1 minus a divided by c, 1 by 3 divided by minus 2 by 3 f, minus 2 by 3 divided by 2 by 3 f is minus f, 3f and minus f is the position of nodal points. Next, principal points, two principal points. There are two principal points P1 and P2, which is at a distance of R1 and R2. So R1, which is d dash minus 1 by c. Here the refractive index mu input is equal to mu output be same. Therefore mu I by mu naught is equal to 1. Therefore the position R1 is equal to d dash minus 1 by c, which is equal to 3f, and R2 1 minus a by c, again which is equal to minus f, which is same as the nodal points 3f and minus f. Therefore R1 is equal to T1 and R2 is equal to T2, means nodal points to principal points P1 and P2 are equivalent with the two nodal points N1 and N2. Now in the figure we can locate these cardinal points. That is the field length, that is the eye length, distance between field length and eye length 2f, that is the incident light, that is the principal point P2, here be the principal point P1, first focal point, this one is the second focal point, from that of lens. And again the nodal points are coincide with this, so P2 is same as N2, sorry, P1 is same as N1, P2 is same as N2. This P2 is at a distance of f, as we say here, that is P2. That the distance here f by 2, that is the second focal point 1 by 2, 3 by 2 f, so 3 by 2 f, the second focal point is the first focal point, maybe the 3 by 2 f, the focal length of that field length is 3f, the second principal point is at a distance of f, and here 3f, with the focal length of field length, and 2f is the focal length of eye length. Okay, these are the position of cardinal points. By using the concept of system matrix, the components, I calculating the equivalent focal length and location of cardinal points here x1 and x2. Look here x1 and x2, I just write that is the focal points f1 and f2. That values of their distances x1 and x2 from field lengths and eye lengths. Similarly, for case of nodal points n1 and n2, these are the nodal points. Here I use the refractive index are same, input and output plane, and these are governed by the distances T1 and T2 from field lengths and eye lengths, Similarly, for principal points, that is P1 and P2, first principal point and second principal point, again these are governed by the distances that is R1 and R2 from field lengths and eye lengths. R1 is the distance of the principal point P1, R2 is the distance that of principal point P2. In this way, we locate all the cardinal points in that of Huygens eyepiece. So, with the help of this visual lecture, we understand what is eyepiece, one of its type, that is Huygens eyepiece, its construction, field lengths, eye lengths, its separation, how image is formed, and location of image formed here. Working of Huygens eyepiece, condition for chromatic aberration, condition for spherical aberration, optical separation between the two lenses, distance of field lengths which is u, object distance from the image I1, then position of crosswire. By using system matrix, we calculate the equivalent focal length and then locations of cardinal points, two focal points f1 and f2, two nodal points n1 and n2, and two principal points p1 and p2 are calculated according to the concept of locating cardinal points by using system matrix. These are the positions or the locations of cardinal points in case of Huygens eyepiece. So, with this useful and informative notes, let me wind up this session. Thank you.